Recall the three principles of modern cryptography: definitions, proofs, and assumptions. We've already spent quite a bit of time building up definitions of secure encryption, both for the case of perfect secrecy and then for our relaxation of computational secrecy. We've also seen a little bit of proofs. We had, in particular, the proof that the one-time pad encryption scheme satisfied our definition of perfect secrecy. We haven't yet had the opportunity to explore the use of assumptions. In the last few lectures, we've defined computational secrecy and talked about how by relaxing the definition of perfect secrecy, we can hope to circumvent the inherent lower bounds and impossibility results that perfect secrecy comes with. We've also defined or introduced the pseudo one-time pad encryption scheme. And our goal in this lecture is to rigorously prove that the pseudo one-time pad encryption scheme meets our definition of computational secrecy. Unfortunately, we're unable to prove this statement unconditionally. We can't prove unconditionally that the pseudo one-time pad encryption scheme is computationally secret. For one thing, such a proof is beyond our current techniques. As I've mentioned several times already, proving unconditionally that some encryption scheme, which is not perfectly secret, is computationally secret, would imply in particular a proof that P is not equal to NP, a long-standing unresolved question in complexity theory, which seems completely beyond our current techniques to address. There's also something a little bit more fundamental than that, which is that the pseudo one-time pad encryption scheme, as we defined it, depended or was defined based on some underlying component G. G was a function that took a small input and produced a larger output. In the case of the pseudo one-time pad, it took as input the key that the two parties shared and expanded that into a pseudo pad that the parties then XOR with the message to encrypt and XOR with the ciphertext in order to decrypt. So we can't really hope to claim anything about the pseudo one-time pad in general unless we know something about the particular G that we use with which to instantiate the scheme. So security of the pseudo one-time pad must depend somehow on what particular function G we plug in, or what properties that function G has. So what we can hope to prove is security of the of the pseudo one-time pad encryption scheme under the assumption that G is a pseudo-random generator. This actually tells us a couple of things, right? First of all, it tells us that if we begin with a pseudo-random generator G, and then build the pseudo one-time pad encryption scheme from that, then the scheme is secure. It also tells us that we can feel free to swap in different functions G. We can put in any function G that we like, as long as it satisfies the property of being a pseudo-random generator. And given that assumption, the scheme will be secure. Now, before we turn to details of the proof, let me just revisit the definition of pseudo-random generators in a little bit different form than what we've seen before. I want to go through it actually in pictures, because part of the proof of the pseudo one-time pad encryption scheme is going to be by picture. So remember that we have some fixed function G, which is an efficient deterministic function, and let's assume for concreteness that G is length doubling. So that means that its output is twice the length of its input. We can now view our function G as being involved in an experiment of the following form. Somebody comes along with an algorithm D. D here stands for distinguisher. This algorithm D takes as input a string Y and outputs a bit B. And we can think of this as D taking as input some string, some long string, and trying to determine whether Y was chosen uniformly at random or whether Y was output by running the pseudo-random generator G on some uniform input. So that means that in one case, we have Y being sampled uniformly from strings of length 2n, and we can look at the behavior of D when it's fed with a string Y sampled according to that distribution. So in particular, right, we can calculate the probability with which D outputs 1, right, the probability with which B is equal to 1, where that probability is taken over the choice of Y according to the uniform distribution on strings of length 2n. and also over any randomness internal to the algorithm D itself. We're allowing the possibility that D itself can be a randomized algorithm. So we can compute that probability. It's a well-defined probability for each value of the security parameter n. Alternately, we can look at a second case. We can look at the case where what we have is an experiment in which we first sample a uniform n-bit string, k, and we then feed that as input to our function g, and take the output, call it y, and feed that to our algorithm d. So now we can again look at the probability with which d outputs the bit b equals 1, where the probability is now taken over the uniform choice of k, chosen uniformly from strings of length n. And again, that's a well-defined probability for each value of n. If g is a pseudorandom generator, that means that for any efficient d, any efficient distinguishing algorithm d, the probability that d outputs 1 in the first case, when y is sampled uniformly from strings of length 2n, is very close to the probability with which d outputs 1 in the second case, when we sample k uniformly and then compute y equals g of k. That's the definition of what it means for g to be a pseudorandom generator. It's a pseudorandom generator if and only if this holds for any efficient d. Before going into the details of the proof, I wanted to discuss at a high level how proofs by reduction work. Proofs by reduction are very common, and we'll see them very frequently throughout the rest of the course. Here I'll walk through a high-level description of how the proof by reduction is going to work for our specific example with the pseudo one-time pad based on a pseudorandom generator G. What we do is we start with the assumption that G is a pseudorandom generator. Then let's say, or let's assume toward a contradiction, that there's some efficient attacker A who breaks the pseudo one-time pad scheme. Where by breaks, I mean very specifically that it violates the definition of computational security. Right? That means we have an efficient attacker A whose success probability in the experiment that we defined is not bounded by 1/2 plus a negligible function. What we'll then do is use this algorithm A as a subroutine to build an efficient algorithm D that breaks the pseudorandomness of G. And here again, I mean breaks actually in a very formal sense in terms of the formal definition of what it means for G to be pseudorandom. Now what we'll do is we'll relate the probability with which D can break the pseudorandomness of G to the probability with which A can break the security of the pseudo one-time pad encryption scheme, and show that if A indeed breaks the pseudo one-time pad scheme, then D breaks the pseudorandomness of G. But we know, by assumption that G is pseudorandom, that no such distinguisher D can exist. There cannot be an efficient D that breaks the pseudorandomness of G. This is again by our assumption that G is a pseudorandom generator. And this implies that our initial assumption about A must have been false, and there could not exist such an A in the first place. One important point here, and we'll see it again later on during the actual proof, is that we don't make any assumption whatsoever about how A works. The only thing we assume in step 2 is that we have some A who somehow or another is able to break the pseudo one-time pad scheme. And we show that the existence of such an A would imply the existence of a D that breaks the pseudorandomness of G. And again, because no such D can exist, that implies that no such A can exist. An alternate way of viewing what we just said is rather than working by a proof toward a proof by contradiction, as we did on the previous slide, we can work in the other direction. So this is really just a reframing of what we had on the previous slide. What we can do, and this is actually more along the lines of the proof we're actually going to show. Again, we'll start with the assumption that G is a pseudorandom generator. We'll then fix some arbitrary efficient A attacking the pseudo one-time pad scheme. Here we're not assuming anything about the success probability of A in attacking the scheme. We're just given that it's some arbitrary A who is efficient, i.e. running in probabilistic polynomial time. We then use A as a subroutine to build an efficient distinguisher D attacking G. And as before, we're going to relate the distinguishing probability of D in attacking the pseudorandom generator to the success probability of A in attacking the pseudo one-time pad scheme. By assumption, right, by the assumption that G is a pseudorandom generator, and because D is an efficient algorithm, we know that the distinguishing probability of D must be negligible, right? The gap between the probabilities with which D outputs 1 in the two cases must be negligible. Using our relation between the distinguishing probability of D and the success probability of A, we will then directly conclude a bound on the success probability of A as desired, i.e. we'll show immediately, directly, that the success probability of A can be at most 1/2 plus a negligible function. This will make more sense after we complete the analysis of the reduction in the following few slides. Let's recall the pseudo one-time pad just so we have it in our minds as we go through the proof. We have the two parties sharing an n-bit key that I've denoted here by k, and to encrypt a message of length 2n, what the sender will do is to pass k as input to G, take the resulting string, the output of G, which is a string of length 2n, and XOR that with the message, and this gives the ciphertext. The theorem we're going to prove is that if the function G, used in the previous slide, is a pseudorandom generator, then the pseudo one-time pad, i.e. the encryption scheme from the previous slide, is computationally indistinguishable. Here's the reduction. So again, we're going to take some arbitrary algorithm A, adversary A, who runs in probabilistic polynomial time. This A is attacking our pseudo one-time pad encryption scheme. We know nothing about how it works, we know nothing about what it does, we don't even know a priori anything about its success probability. The only thing we're given is that it's efficient and that it is trying to attack the pseudo one-time pad encryption scheme in the sense of our definition of computational secrecy, which means that this adversary is going to output a pair of messages, be given back a ciphertext, and then output a bit with which it's trying to guess which of those two messages that it output was the one that was encrypted. We're going to construct from this A distinguisher D that uses A as a subroutine. So I've drawn the picture here as if D is you can think about it as a black box that contains A inside, or you can think about D as some piece of code that makes subroutine calls out to the function implementing the attacker A. Either way, we imagine in this picture that A is being run inside of D as some kind of a subroutine. D is going to be a distinguisher trying to distinguish whether it's given uniform strings or strings that were output by the pseudorandom generator G. So the interface of D is that it's going to accept strings Y as input and then going to output a bit B, or a bit rather, just determining whether or not it thinks that its input was uniform or the output of the pseudorandom generator. D works in the following way. What D is going to do is start running A as a subroutine to obtain two messages M0, M1. These are the two messages that A selects. At this point, D is going to simulate the experiment of computational secrecy for A. So what that means is that D is going to, on its own, sample a uniform bit B, determining which of those two messages it's going to take, and it's then going to XOR the message M sub B that it selected with its input string Y. We can call that C, just a variable name, but it's meant to indicate that we're thinking of this as a ciphertext, and it gives that ciphertext as input to A. So remember, A believes it's attacking the pseudo one-time pad encryption scheme. So from A's point of view, this exactly matches what it expects to see, because A indeed output two messages and got back a ciphertext. A will then output some bit, B prime, which is supposed to represent its guess as to which of the two messages were encrypted. And what D then does is to check whether or not B and B prime are equal. Right? D chose B itself. D got B prime as output from the attacker A. So D can certainly check whether those two bits are equal. And D will output the bit 1 if and only if B and B prime are equal, and 0 otherwise. So this completes our description of D. D is well defined, given any algorithm A as a subroutine. The first thing to look at, or to check, is that given that A runs in polynomial time, so does D. All D is doing is running A once as a subroutine, and then doing some very minimal processing on top of that. So if A indeed runs in polynomial time, then so does D, i.e. if A is efficient, then D is also. In the analysis of the distinguishing probability, the distinguishing gap of D, it's useful just to define as a piece of notation the function mu of n to be equal to the probability with which A succeeds in the computational secrecy experiment. Right? Remember that we defined this experiment priv_k in an earlier lecture, and basically this corresponds exactly to the probability with which B is equal to B prime when using the pseudo one-time pad encryption scheme. So pi here refers to the pseudo one-time pad encryption scheme. So first of all, we can look at what happens when the input given to D is pseudo-random, meaning that we determine the input to D by choosing a uniform seed, giving it to the pseudo-random generator, calling the result y, and then giving that value as input to D. If the input y is generated in that way, then I claim that the view of A, when being run as a subroutine by D, is exactly identical to the view of A in the experiment priv_key A pi. And I'll show that pictorially on the next slide, but assuming that's the case, that means that the probability that D outputs 1 when y is generated pseudo-randomly, i.e. when we generate the input to D by choosing a uniform seed x and then computing g of x and feeding the result into D, that probability is then exactly equal to the probability with which B is equal to B prime, which is exactly by definition equal to the probability that A succeeds in experiment priv_key A pi, which we define to be mu of n. So let's look at this claim that when the input y is pseudo-random, the view of A is exactly the same as an experiment priv_key A pi. So here's the picture, similar to what we had 2 slides ago, although now I've changed the way, or I've explicitly denoted rather, the way that y is being sampled. So here we're working under the assumption that we're in the case where y is sampled by choosing a uniform seed k, running it through G, and letting the output be denoted as y, and feeding that in as input to D. Well, in that case, if we just draw our box a little bit differently, we see that inside this top box that we just put here, this corresponds exactly to an experiment where A outputs 2 messages, a uniform bit is chosen, and then if you look at the what's going on with M sub B, where we have it being XORed with this string y, that is exactly syntactically identical to what we would get if we chose a uniform key k and then used the encryption scheme of pi, i.e. the encryption scheme of the pseudo one-time pad, to encrypt the message M sub B. Right? You can take a look at that again. So here where we just have the picture where we take key, run it through G, get a string y, and then XOR that with M sub B. But remember that that's exactly what we do in the encryption scheme for the pseudo one-time pad. So we can replace that with a box for encryption in the pseudo one-time pad. And this picture here is precisely the picture of the experiment priv_key A pi. Right? Again, A is outputting 2 messages. One is chosen uniformly at random. It's then encrypted using the encryption scheme of pi and a uniform key. The ciphertext is given to A, and then we look at whether or not A, at the bit B prime output by A. And we know that the probability with which B is equal to B prime is by definition the success probability of A in attacking pi. And that's what we said a moment ago. For the next step, we look at the other case. We look at what the behavior of D is when its input y is chosen uniformly at random. Well, in this case, I claim that A will succeed with probability exactly 1/2. So that means that the probability with which A's guess B prime is equal to B is exactly 1/2. Because D outputs 1 only when B is equal to B prime, that means that the probability with which D of y outputs 1 when y is sampled uniformly is exactly 1/2. And we can look at this picture as well. So here I have the same picture, but now sampling y as a uniform 2n-bit string. And if we draw our picture again a little bit differently, and replace this part here with encryption using the one-time pad scheme, right? Not the pseudo one-time pad scheme, the one-time pad scheme, because now the key y here is uniformly random, a uniform 2n-bit string. So then this is exactly a picture of the experiment in which A is attacking the one-time pad encryption scheme. But we know that the one-time pad encryption scheme is perfectly secret, and that's stronger than being computationally secret. So we know that the probability with which A can output B prime equal to B in this experiment is precisely 1/2. Now we're almost done. So we've determined, or we've related the probability with which D outputs 1 in each of those two cases to, in one case, the probability with which A succeeds when attacking the pseudo one-time pad, and in the other case we've explicitly calculated it to be equal to 1/2. Now by the assumption that G is pseudo-random, and because D is efficient, because D is polynomial time, we know that the difference in probabilities with which D outputs 1 in those two cases must be bounded by some negligible function. Or more exactly, the absolute value of the difference has to be bounded by some negligible function. So there exists a negligible function, epsilon n, such that mu of n minus 1/2 absolute value is at most epsilon n. And just substituting in terms and rearranging and doing some algebra, we see that this implies that the success probability of A in attacking pi is bounded by 1/2 plus epsilon n, for epsilon n a negligible function. And that completes the proof, right? What we wanted to show is that the pseudo one-time pad encryption scheme pi meets our notion of computational secrecy. We showed this because we started with an arbitrary efficient algorithm A and proved that regardless of what A is doing, as long as it's efficient, there's some negligible function epsilon such that the success probability of A in attacking pi is at most 1/2 plus epsilon. So let's step back a little bit and ask ourselves what this all means. So importantly, we've now proven that the pseudo one-time pad is secure. The point, again, being that we have a provably secure scheme, which is much better than having a heuristic construction that just looks secure or one that we don't see any obvious way to attack it. On the other hand, this proof does come with some caveats, and I don't want to downplay these. So the proof is under the assumption that G is a pseudorandom generator, and of course the proof is always relative to our definition. So what we proved is exactly what the theorem said, which is that the pseudo one-time pad achieves our notion of computational secrecy. Now what this means is that on the one hand, we're guaranteed that the only ways to break our scheme, or to break the pseudo one-time pad scheme, are either to find a weakness in G, or if the definition of computational secrecy isn't sufficiently strong. The first of these, a weakness being found in G, is a concern in practice. However, for the most part, what an implementer would do is choose some standard algorithm G, which is widely believed to be a pseudorandom generator, and it's therefore relatively unlikely that weaknesses will be found in G. This is obviously more true when G is something that's stood the test of time and been around and analyzed a lot longer, but nevertheless, it's relatively speaking unlikely for weaknesses to be found in G. And moreover, if a weakness is found in some particular function G, then the implementer can always swap out that function G for another function G prime that's believed to be more secure as a pseudorandom generator. More problematic is the issue of the definition. So the definition of computational secrecy that we've been using, in fact, isn't really strong enough for most applications of cryptography in the real world, or most applications of encryption in the real world. And this is a real issue, and one that we're going to start exploring in the next lecture.